Okay. All right, well, yeah, it's dangerous to ask Jared about predictive control because the answer will just go on and on and on. My name's Laird Close, and I'm another lifer. I was at the original LEO meeting, and I gave a talk about the GMT and imaging exoplanets with the GMT, and I'm here again talking about the GMT and imaging exoplanets. So, but what I really want to concentrate on, Jared gave you a good overview of GMagAO-X. I'm going to be talking more about MagAO-X, and which is our pathfinder, which is it's a full instrument that has been doing really good, really exciting science for the last few years in the visible. I'm going to particularly focus on the visible here. We haven't heard a lot about adaptive optics in the visible. I've met some people at the conference should say, oh, nobody actually does adaptive optics in the visible, but no, it's a thing, and it's quite powerful. For example, we've seen lots of images of young objects, and we've seen these beautiful cleared cavities that we see from ALMA, and if we image them in a continuum wavelength in the visible, they kind of look like this. But as there's gas flowing through these cavities onto the stars, some of that gas along the way falls onto planets, which is great because that allows these giant planets to grow. And it also lights them up in the wavelength of H-alpha. And I thought about this in 2014. I wrote a small paper saying, oh, actually maybe H-alpha is the easiest wavelength in the visible to detect young planets. Nobody really thought much of it at the time, but it's gone on to be actually kind of a neat technique, this H-alpha planet technique. And this is MagAO-X, and same photo that you just sort of saw. There we are on the 6.5 meter Magellan telescope. So this is located at the Las Campanas Observatory. It's an extremely good site, okay? This doesn't work if you're in a mediocre site. You need a good site, otherwise you're not going to be able to do adaptive optics in the visible. And there's our amazing team. You also need a wonderful team at the wonderful site. And everybody that has a name here is at the meeting, hopefully in the audience. And they all have posters and talks. And Jared went over quite a few of those points. All right, well, there's me by the instrument, kind of for scale. It's super complicated. And I love that Jared gave a whole talk and didn't even really mention the instrument that he's PI of, and it's simply a wonder. The AO correction that we had at the first Spirit of Leo conference was so, this would look like science fiction. And to try to prove that, I'm just going to show a little movie here. And if you believe in magic, this is about as close to magic as you can get. There's the loops on. And here, sorry, I want to go back. I want to run that again, just as pretty cool. And, oh no, hold on. I think I can get this to sync up. Here we go. There we go. And then we're going to turn the loop on, and the arrow is pointing, obviously, to the real companion. The other things are DM speckles, but you can see this is like 27 milliarc-second imaging, real time. This would almost be as if you were looking through the eyepiece. This is what you'd basically be seeing. It's a little redder than that, but this is visible light, adaptive optics, high strels, up into the 60s, 70s at these wavelengths, and extremely good wavefront correction. This is what a deep image of the PSF would look like. This is the bottom of the instrument. It's a double-decker. There's all the DMs are on the top level. It's complicated. I'd love to talk more about it, but I don't have the time. But come and talk to me more about it later. But it's a fully PSCMC, LEO, chronographic thing with 3 deformable mirrors. First one's a woofer, and then we have a tweeter, and then we have a cleanup NCPDM, whose only job is just to make sure that we get the very highest strels in the science camera. And that has proven to be really important. Okay, so let's do some science. Let's go to PDS-70B and C. These were basically the most well-known H-alpha planets. So the images I'm showing you here are the dust, and the star has been subtracted away because I've subtracted off the continuum image, and all you're looking at is the difference, the so-called SDI image. So we've removed, it's just pure H-alpha emission. And what you're really seeing here is a progression from the basically first light commissioning over to where we're really getting good science going. We're correcting 200 modes in NCP. We're going at a kilohertz. We're correcting 650 modes. We have no read noise because we're using EMCCDs. And at this level, this is an H-alpha imaging machine. Like, I don't think anything else on Earth or in space. And you know, what can you do with something like this? Well, you can actually see the scattered light coming off of the CPDs around the individual objects. So that's sort of what an artist's illustration would look like. That's drawn by my daughter because that's all I could afford at the time. So she did a good job on that, though. And you know, so the idea is that you're seeing these bright scattered things, and this is the forescattering off of the front of the individual CPDs around the planets. I got to go a little faster here. This is kind of the idea. They're variable. Over time, you can see that at H-alpha, the planets actually are not steady. They flicker a bit, and that's not too surprising, as anyone who's studied magnetospherical accretion. These are very small things. These disks are only on the order of about 30 milliarc seconds. So you need very high resolution. We found a bunch more of these planets. Jialin Li has a very nice poster. I think it's number 36. Go outside and see her poster. And she has this nice detection of a new protoplanet in 2-mass 1612. Moving along, Rochelle already talked about WISPIT-2. There's the beautiful image in polarized light. When you look at it at H-alpha, you can see a beautiful, strong detection. This actually how we discovered the planets was at H-alpha. We knew about the disk, and then we saw that there's actually these beautiful, strongly emitting H-alpha planets, and that's very exciting. This is what this is sort of our technique. You know, you look in the continuum and you see nothing, and then you look at H-alpha and you see something, you get excited, and then if you're me, then you don't go to bed and you load up your Jupyter notebook and you run your Python data reduction code and you're like, ooh, I think I see something. And then you observe it again like 2 nights later, and you spend more time on it and you pull out a beautiful 12 sigma detection of an H-alpha planet. And that's what it looks like at L-band too, so it's nice to see at L-band. ALMA's also imaged it, absolutely beautiful image. Doesn't quite show all the structures we see inside. And I think the other thing that's kind of exciting is it's 2 planets. It's WISPIT-2b and what I called CC1 in my paper, but you can call it now 2c. Here's my favorite image of all. You know, it's pretty, well, I made it, so I'm really biased, but you know, this is like, I think this is, you know, this is what young solar systems kind of look like. Probably all of them maybe look a little bit like this at some time in their evolution, but this is a particularly amazing example. And WISPIT-2, I think, is probably, in my mind, the most exciting exoplanet detection we've done in a while, and it's just super exciting. Rochelle should be congratulations for discovering this amazing system. It's so great, you know, 2 planets, 4 rings, cavities, gaps. It's very exciting. But we're going to move on. We can see that over time, mass accretion rates also vary. That's maybe not too surprising. These are all the known H-alpha planets to date. The other thing that might be a little surprising is that when we look at these things, they all kind of look a little similar. They also have sort of similar fluxes at H-alpha. They could really be, I predicted that they would be maybe 100 times brighter than this, but they all seem to be about the same level. So they're just barely accreting. These are very low accretion rates. They're just at the very tail end. And the other thing that's kind of interesting is that all of the planet inclinations, at least if you take the ALMA inclination of the ring in dust continuum, if you take that as the inclination angle, then you sort of convince yourself that most of these objects, I've just plotted them all as a function of inclination, they're all kind of hanging around 45 degrees. So we're not finding, like we've just seen a few beautiful face-on disks, but we're not seeing a lot of H-alpha from, for example, 169.142b. I think Miles was directly asked that question. Where's the planet? You got this beautiful face-on ring and a gap. Where's the planet in the gap? Why don't we see it at H-alpha? I don't know. So, you know, we don't have very many objects. This could be over-interpolating a small sample, but maybe inclination matters. Maybe magnetospherical accretion is coming along the field lines. Maybe there are some angles where you can see down into the actual H-alpha forming area here. This is where the H-alpha is coming out. And maybe this is the key, is that some inclinations will work better than others. If you look just straight face down, you might not see that because of the strong cloud formation that could cause from having the hot plasma from the impacting infalling gas. So anyways, it's kind of a little complicated, but it's an interesting picture. There could be some, there's some truthiness to this idea, and it's something that really needs to be explored more. I was listening to Jonathan's great talk this morning, and I was thinking, yeah, no, this is all good. I really like what Jonathan's saying, but no one, I don't think, really models this problem, is that you've got something to the equivalent of 1 trillion atomic bombs going off in the atmosphere all the time on young planets. And that's really going to stir things up. And so that's an interesting thing. And I think it'd be interesting to see how that affects KZZ. But so what I showed you up until now was all without chronographs. So not in the spirit of Leo, but in the spirit of Leo, we're starting to do chronography at H-alpha. And what you can see here, I'm just sort of going through the instrument showing, we start here, you can't see the core of the star, that's before the chronograph. We go through the Leo chronograph, we use a LOFIS, we split off almost all the light, send it into the LOFIS with a reflective mask, sorry. And then we block the Leo here with the undersized stop. That was our pre-appetizer. This is the main Leo stop. And then we get these nice images. These are real H-alpha images of a real star. And you can see that basically you take a whole bunch of continuum images, you subtract them from a whole bunch of H-alpha images, and you wind up with your final ASDI image here at the end. And that is where you find your planets. And that's what we're doing now, and that's kind of exciting. And nobody can read this, it's too small, sorry. But this is our new survey. We're basically going from these sort of in green, you can see here, these are where we've detected things. And we found planets around most of the big cavities that Alma said we should find planets in. And now we're pushing down into these chronographic surveys. We're getting down into these really much, much tighter planets at 100 milliarcseconds or smaller. That's the future. And the future for us, anyways, is the so-called H-alpha Protoplanet Survey HAP. And so this is, we're just starting that. I saw this plot the other day, and I was like, oh, this is sad because gravity was built. It's such a nice instrument, but it's got no planets to detect. So what I want to do here is just show a few planets. No, I'm just sort of kidding here. Vanessa made this wonderful plot, and I just put up, these are where the H-alpha planets live, and these are all the H-alpha planets to date. And it kind of fills out this little part of parameter space. Yes, it's not habitable planets in terms of 10 to the 10 contrast, but it is really very interesting because these giant planets will set up sort of future habitability in these solar systems. So they're super exciting to study because these planets can set up pressure bumps and they can clear out the gas in the inner part, give you terrestrial planets at 1 AU. They're super worthwhile studying. And this is a really good window. So these are all about 5 mega years old. So this gives us our insight into what planetary systems are doing at 5 million years. Here's a bunch more of these HAP1, HAP2, HAP3, HAP4. Anyways, I don't really have time to go into all of those new things. I don't have time to work on the data. And of course, Jolin Lee, my graduate student, is super helping me with all of this as well. And then, of course, we pivot to the giant Magellan. I just thought it's kind of fun to see how this all kind of fits in. There's where all the data is that I've been showing you from the Magellan telescope, and then we just go up the road, and this is where, well, this is an artist's illustration, of course, where the GMT telescope would be, and this is the actual rendering of the enclosure. Jared talked already a lot about this, but it is kind of exciting. He showed you a better movie, so I'm going to skip over that. Jared was kind of showing you a lot about how we can kind of work around habitable worlds around M stars, whereas, future space telescopes like Haberolds will do it around G stars. This is where we're going to live with GMagAO-X. So Jared didn't show you very much in the way of optics. Optics are so important, and I just wanted to show you the optical layout. Again, in the spirit of Leo, we got to talk about these things. And so, well, it's a lot. Anyways, it's talk to me if you want to know more about the parallel DM or woofer or our wavefront sensors. But we have a plan. It's just a scaled up MagAO-X, but it should work. And here we are at the conclusion.
Laird's enthusiasm for all things H-alpha clearly shone through in that talk. And perhaps that what will that do to KZZ, maybe the quote of the conference. I think we have time for maybe one quick question before we go to our survey. Or perhaps everybody can just talk to Laird. Oh, yeah, go ahead, Annika.
Very quick, there was a slide where you showed MagAO-X images of PDS-70B and C over time. The 2024 image had something really bright closer in. Do you know what that is?
The PDS-70. Yeah. So that, okay. Oh, well, anyways, it's, okay, that is, I think, okay, so there's been a lot of talk about PDS-70D, right? And this has a very similar PA to PDS-70D. There's, I think the real question is whether that, I see continuum there too. So that is not to me a pure H-alpha object. I think that there could be a dust feature there. There's something there, but I don't think it's necessarily pure H-alpha. I think it's a bright dust knot, but it might be a planet too that's just not very bright at H-alpha. All right.
Thank you very much, Laird, and let's thank all our speakers from this morning.